but I'd like to welcome you to today's webinar on how coatings can reduce downtime and increase mean time between repair in the mining and ore processing industry sector. In previous webinars, we've used the chat room for an identification area where you can type in questions. And if the question can be easily answered within the context of the discussion, I'll do my best to answer it at that time. If it's a little bit more detailed question, I may postpone it to the end, and then those people who are interested in the answer can stick around. At the end of the webinar, we will also be asking you to complete a brief survey, which will be posted up in the chat room, and you'll be able to hyperlink to that webinar area and access the questions and answer online. We'll keep the meeting session open until we get a response. With that being said, let's get started. We've got some meaty material to go through, but hopefully it'll be very interesting and beneficial to you folks. The basic agenda is we want to go over and understand the typical abrasion wear rates in various phases of the extraction and processing of mineral ores. These mineral ores can be metallic, non-metallic, fuel-based ores, you name it. We also want to identify the various types of wear, be able to visually identify and also describe them so you can understand how they impact the equipment. Then I'm going to focus on some of the critical characteristics of the various coating technologies that can have an impact on improving the mean time between repair of your process equipment and structures. And then we'll look at various types of coatings and their attributes and identify the targeted areas where they can be used for consideration. Because it's quite a reality that there are numerous different wear and corrosion resistant technologies that are available to the materials engineer to assist in increasing reliability and production output for the plants. So let's get started. First thing we'll look at is the basic areas of wear, where occurs in the ore processing phases. To the far left, you'd have the extraction, which can be underground mining, open top mining, open pit mining. Those are areas that are going to be dealing with much more coarser, heavier, larger particle sizes, raw ore and rock, and the associated waste product, as well as topsoils. When we move into the ore processing areas, things become a little bit more controlled. In the very bottom section of this slide, you'll see there are areas where wear rates are quite high, such as the grinding area. This is where you have a lot of particle size attrition. There's large particles being crushed into smaller particles, being crushed into finer particles still, all as a process to liberate the valued ore product from the gangue or the waste product. There are slightly lower wear rates that you might see in the crushing phase. This is where you're doing primary crushing, getting it down into the size ore where you can grind and liberate. In the crushing phase, we're really not liberating ore, we're just breaking the large rocks down into those smaller ones. And then you'll see finer and finer wear rates, where the wear rates are typically less than 5 grams of loss per 1,000 tons of ore processed. So the primary areas we'll focus, where you'll see heavy wear will be grinding and crushing, and then lower wear rates in the screening and the pumping and the classifying and separation phases. Now, when we look at the various types of wear, there are levels of severity and degrees of wear, as well as locations where you'll see those degrees of wear. The most severe is what we would call gouging abrasion. This would be common in the primary crushing phases in the ore refining and processing side. But in the extraction, this is where you would see it in the bucket loaders, the front end loaders, the drag line buckets, things of that nature. This is common where your ore size is quite large, typically greater than 10-inch in size. It involves a cutting and tearing effect on the surface. Essentially, the ore is plowing a furrow through the base metal. And typically, this can also involve some high impact along with bending stresses as well as high compressive loads. The areas where you would see this commonly would be in your gyratory and jaw crushers. You may also see it in sag mills, and again, as we said, in the dragline chutes, dragline buckets and front end loader buckets. This is a very high wear area. The next area where you see severity is the high-stress grinding abrasion. This is also sometimes categorized as three-body abrasion. This oftentimes will involve particle size reduction passing between two surfaces under high load. So you may see this also in crushers, but you will see this more commonly in the grinding or milling phases. These could be hammer mills, these could be rod mills, these could be ball mills. There may be some impact, it'd be limited to localized area. but it occurs when particles are crushed between two spaces and you are liberating smaller and smaller particle sizes. So you're continuously exposing new sharp edges that can cut, grind, and damage the base metal. The third area of attack is called low stress scratching abrasion, also classified as two-body abrasion, and this normally involves particles moving freely across the surface under minimal load. On a micro scale, this is similar to gouging abrasion, but it is cutting much finer, coarser, much finer creases through the metal, leaving micro gouges. There is normally minimal impact, but there may be high velocity, and this would be in applications that you would see. This would be in your chutes, your cyclones, screens. You may also see it in pumping situations, in areas where slurry pump situations. And the final area of attack that we sometimes see is an area known as erosion corrosion. This normally involves much finer particles that have been liberated from the raw ore. They can be present in a wet, such as a slurry matrix, or they may be pre-processed in a dry area where it's being conveyed by screw, or where it's being conveyed by conveying system, or drop chutes. Normally this is a lower mechanical stress and there'll be minimal impact, but we would see this typically then in those pumps and agitators and cyclones. And you've been able to identify and see the forms of wear as they occur on each one of these pieces of equipment. So those are your primary modes of attack that we're going to see. Now, when we want to classify the rate and the degree of severity and how each one of these characteristics has an impact on it, I want you to look at this table here. And what this shows you here is on the left, on the vertical column, you'll see the size of the abrasive particle, the impact force that's being resulting, the total true stress force that's being resulting, the velocity of flow, the impingement angle of the flow onto the surface, any other environmental factors that come into play, whether it's dry or wet, or if it's a high pH or low pH, and the principal mechanism of damage occurring. So you can see for something like gouging abrasion, the primary mechanism is plowing or cutting wear. So if you see, if you're dealing with high stress grinding, it tends to be more of a cutting and fragmentation wear. When you get into low stress scratching, it's more cutting and corrosive wear. And when you get into erosion corrosion, it's similar to the low stress, but you also have to add in the plowing, fragmentation, and corrosion factors. So these are all properties that come into play as you start to impact the different types of coating situations that you might want to select. Now, factors that can influence the behavior of various materials in here. When you're looking at the abrasive particle size, the contact condition that we're dealing with here is the force and impact at the point of contact. And there, the desired wear material properties could typically be hardness. The harder material, the better the wear resistance might be. Another example might be the opposite of that, where you're looking for more ductile applications in a high degree angle of impact, 90 degrees or so. Anywhere from, say, 75 to 90 degrees, there you might want a softer system, such as a rubber. Particle shape also is an impact. Here, the velocity and the velocity which that particle is impacting the surface will have an impact on the yield strength of the substrate. And then you get to some of the other ones, such as hardness, which will also have an impact on the impingement angle. And there you're looking at more the elastic modulus of the base metallurgy or the base substrate. As you look at each one of these abrasive, the properties of the abrasive and the contact conditions, the desired wear material properties are indicated in this table here. So we can use this as a way to define where properties are most beneficial to providing the performance attribute that you're looking for. Now, here's some examples of various materials that might be used in a abrasion or wear application in the mining and ore processing industry. And there are 6 different materials that are being identified here. You have the high chrome alloys. These could be your white irons. These could be your chrome carbide based materials. You have the tooled steels. You have your mild steels. You have ceramics, which are typically aluminous ceramic tile. There are polymer-based materials, which would be reinforced coatings. These would normally be epoxy-based materials. And then you have an elastomer range, which could include rubbers and urethanes, things of that nature. And when you're looking at degree of impact here, the degree of impact is critical here, because you can see when you're dealing with a ceramic-based material, at low angles of impact, you're going to get relatively for the rubber-based materials, you're going to get a relatively high wear at your low angles of impact, and as you move towards the higher and higher degrees of impact force or impact angle, the rubber systems actually have lower wear rates. Conversely, if you look at a ceramic-based material, as you move to higher and higher impact forces, the wear rate increases dramatically. That's due to the brittle fracture nature of these materials. Other materials tend to be more wear hardening in effect. And then you see your polymer-based systems performing roughly in the same range as the rubber range. It depends upon the type of polymer that is being chosen. But ductility in this instance becomes the more primary driving force to resistance and wear. Now, when we go from degree of impact as a characteristic, or how that impact force can derive performance, now we'll look at velocity and how velocity can impact particles moving across the surface. Again, you have the same 6 materials chosen here, and you can see from a standpoint of ceramic performance is best as you increase the velocity across the surface. Ceramics tend to give you the highest wear resistance. The high chrome alloys, the polymer-based systems, they all start to fall out as far as performance goes as you increase velocity. But certainly ceramics provide you very strong resistance to high velocity sliding wear. And finally, when we look at corrosion and chemical resistance, because sometimes these slurries or these abrasive materials, abrasive conditions are present in a slurry or a corrosive solution. These corrodants can be chlorides, they can be sulfates, they could be various acid-based compounds that might be used in the leaching process, and these will also have a high impact on the degree of wear. Because as metals react, or as any material reacts with the chemical environment and oxidizes, it becomes a passive layer. That passive layer is weakly bound, and then flow, particularly a flow with embedded suspended particles, can cause accelerated wear. So in this situation here, ceramics, which are relatively inert to a wide range of chemical compounds, offers fairly consistent wear resistance over decreasing pHs, which would be your acidic range, and increasing temperatures. Conversely, your mild steels tend to perform worse in this type of application. So you want to be looking more at your ceramic-based materials under this type of situation, or you could look at polymers or rubbers depending upon the elastomeric system you're choosing. Is it a urethane-based compound, or is it a vulcanized rubber-based compound? Or in this instance here, from a polymer standpoint, what is the functionality or molecular weight of the polymers that are being used to provide you better temperature and chemical resistance? So those are 3 factors where you can see impact, velocity, and chemical and temperature characteristics coming into play, taking a part in your material selection process. Now, when you're getting to the point of choosing materials, there are various technologies that have been used in the industries for many years. One of the most common is hard facing, and this can employ a welding process using an alloy rod, or it can employ what's known as a thermal spray approach to apply either powdered ceramic or powdered metal or metal rod into a high velocity gas flow, which will liquefy the material and then under high velocity impinge that material onto the surface if it's thermal spray. If it's hard face welding, it's simply laying down rod on top of the surface in multiple passes. Typical thickness of these materials can be anywhere from 40 thousandths of an inch and up. They can be applied as thick as maybe up to 3/8 of an inch. The selection of the material that you would choose would be based on multiple factors, such as the friction of flow across the surface, such as the heat, such as the corrosion resistance and impact resistance. You can choose these high chrome carbide alloys, you can choose marstenetic or austenitic rods, you can choose ceramics, tungsten carbides, chrome carbides. All these different materials will come into play. Variables affecting performance are going to be the hardness that you're looking for, the corrosion resistance that you're seeking, the ability to absorb and withstand heat treating to relieve the stresses, because you are inducing stress into these base metals when you're welding the alloys. You want to make sure you're using compatible alloys if there's a corrosion mechanism in play. And you want to make sure that the alloy materials that you're using have the suitable hardness to resist the wear factors that are going to be into play. There are multiple different versions of this. Here you can see rod being laid down. Here you can see an application on a bucket loader. Here you can see applications on a trunnion housing for a feed into a ball mill. And here you can see thermal spraying onto a abrasion, basically a transport screw used in an abrasion application. So all of these are areas where hard facing, either through the utilization of rod or powdered alloys or metals, being applied for wear resistance. Another technology that's used sometimes are thermoplastic-based materials. These can involve your ultra-high molecular weight polyethylenes, your polyvinylidene fluorides, and your polypropylene-based materials. These are often used when you have chemical exposures as well. These can provide extremely good resistance, and they can be used to line mild steel pipe. They provide great corrosion resistance, fantastic release properties. They can have good ductility and resistance to mild abrasion. Normally, these materials are applied in a sheet which is glued on or thermally attached to the material by fusion. But some of the concerns that we have with these materials is the ability for them to withstand force and resist disbondment and detaching, because when these materials detach, they tend to detach catastrophically, and that can result in downstream pluggages of your process flow. So examples here is a thermoplastic liner to the internal of a slurry pipe or chemical slurry pipe. Here you see materials used in a hopper where you're looking for better release properties. So you don't want hang up on the walls, so your ultra-high molecular weight plastics give you good release characteristics, allowing the material to flow in a mass flow approach down into your process. You also see haulage buckets in off-road trucks being used to get better release of the materials, so you're not getting hang-ups, so the yield of the bucket is much higher. You get better fuel efficiency and better transport efficiency as you move your ores around the plant. And then you can see situations where ceramics are being used. Now, ceramics typically involve either silicon carbide or aluminum oxide based materials. These are chosen because they have excellent low resistance to low stress scratching abrasion and erosion corrosion resistance. These materials are inert materials. They are typically applied in a glue fashion. Sometimes they may be encapsulated into a rubber matrix and mechanically attached onto the surface. But this is a sacrificial wear coating that is intended to resist sliding, low angle of impact wear resistance. Where you do have high impact applications, there the ceramic tile is often embedded into a rubber matrix, so the rubber can actually absorb the high impact stress while the ceramic provides wear resistance. And here you can see some examples of the ceramic tiles that are used. You can see it comes in square shapes, it comes in hexagonal shapes. It may be applied in different contours where you're going from square to round transitions, so that the labor intensity of this type of application is quite high. The installed cost is quite high. But in those applications where you're dealing predominantly with sliding abrasion, low angle of impact sliding abrasion, ceramic systems are quite popular. Now, some of the issues that we find with ceramics is particularly related to the high angle of impact phases, where the brittle nature makes it more prone to cracking. And in many instances, if the tiles are laid and the grout lines wear out, you get grout erosion, and then you get undercutting and eddying, which can impact the adhesive layer, which can then result in tile disbondment. Once a tile is dislodged, if it is in the process flow, it now becomes a potential projectile, which can cause further damage downstream to process equipment or other lined areas. So again, when you want to consider any type of coating system, you also want to consider the mode of failure and the impact of that mode of failure to your process system. Another category of lining systems that are commonly used would be categorized as elastomerics. These systems can include your natural rubbers, your polyurethanes, your polyureas. They're chosen typically first and foremost for their impact resistance, and depending upon the formulation and chemistry, you can get varying degrees of corrosion and temperature resistance. These materials are normally applied in a calendared sheet format. If it's a sheet rubber lining system, and adhesive is laid down, the rubber is pressed out onto that flat surface. The seams are sealed with typically an overlapping seam layer, and that becomes your liner. Polyureas and polyurethanes are liquid applied systems. These can be spray applied, and these also will provide you slightly better corrosion resistance than many of your rubber-based systems, and they can be applied to irregular shapes as well. Concerns of your rubber-based sheet applied materials is seam failure. The seam often is the leak path. That's where typically where permeation or abrasive wear will occur first, and once that undercuts, then the seam is exposed, and then rapid delamination of the surrounding sheet layers can occur. Again, when these materials fail, tends to be in sheet format, and these sheets can then break loose and become part of the process flow, binding up a valve, binding up an impeller and a pump, or a rake arm and a thickener, and cause further downstream damage. So you want to be concerned about the mode of failure with these types of materials as well. Applications you can see here for rubber lining for pipes. Here you can see the actual seam in the rubber lining. If that seam is undermined, this rubber lining can peel back and plug the pipe, as well as the valves downstream of the pipe or pumps. The ability to conform rubber-based systems to irregular shapes such as agitators is quite difficult. You tend to have a lot of hard angles, and rubber lining systems do not like to bind over or bond around hard edges. It tends to be a high wear point. So the ability to contour those materials to irregular shapes such as agitators or baffles is problematic. And the last category of coatings that we'll look at are what we call reinforced coatings. Normally these include a thermoset chemistry such as an epoxy or a urethane. It may also incorporate polyesters and vinyl esters for high chemical and higher temperature resistance. But normally the epoxy is the matrix that is used, or the binder, and then the functional reinforcements for these type of wearing characteristics are normally the same materials that are used in the ceramic-based industry, typically silicon carbides and aluminum oxide materials. These materials can provide high degrees of corrosion resistance as well as varying degrees of temperature resistance, and their ability to withstand abrasive wear is directly related to the amount of ceramic reinforcement. Some of these systems can have relatively high ceramic reinforcements, as much as 85 to 90% on a weight and volume basis, and that gives you an extremely high wear resistance, essentially the same wear resistance as ceramic tile, but you've eliminated the seams and the grout lines that you might see with ceramic tiles as well as with rubber-based systems. So you get the benefits of the rubber and the ceramic without the negative attributes. The concerns we have with these materials is bonding strength and adhesion, and this is directly related to the ability to how surface tolerant they are to preparation and the degree of surface preparation that is able to be achieved. These materials can be applied by spray, they can be applied by trowel, they can be cast as well. And here you see some examples of coating systems. In this instance here you see a coating system on extraction fans or ventilation fans. In the mining industry, here you can see linings being applied to large clarifier applications where you're dealing with a corrosive as well as an erosive flow. Here you can see slurry pipe sections lined with a ceramic reinforced epoxy system. And you can even see applications where ceramic-based materials have been incorporated into various filament-wound thermoplastic-based materials, such as filament-wound pipe applications. And in this instance here, the ceramic liner is actually into the structural matrix, so it provides wear resistance. And this is a benefit when you're looking at weight reduction or chemical slurry applications. So there are numerous coating technologies that are out there for you to consider. Here you can see an application on a vibrating screen application, and a high ceramic loading system is being used in the transverse structural members, and on the areas where it's exposed to more corrosive flow, a thinner film coating system has been used for more corrosion resistance, whereas a highly ceramic reinforced system is used for wear and abrasion resistance. Now, when we're looking at where coating materials will be used, depending in the operation or the process area, you'll define the type of wear that is occurring, and then you can choose the various materials. So this table here gives you the ability to look and say, okay, if I'm in the screening area, the typical wear that I'm dealing with is gouging wear. There is little high-stress grinding wear, but there is low-stress scratching abrasion, and there is erosion corrosion. So in that area, the use of hard facing, which could be metal-based welding, or thermal spray systems could be used. You can use the whole range of elastomers, which could go from rubber sheet to polyurethane and polyurea, and you can incorporate reinforced coating systems. It'll come down to cost, degree of difficulty, impact to performance. All of these factors will come into play as well, but from a pure materials performance characteristics, any one of those three systems would be advisable and suggested. Likewise, you move to a pumping application or classifying application. As you move downstream in the process area to a finer and finer particle size, the use of elastomers and reinforced coatings becomes more prominent. In the front end of the application, digging and extraction and loading and hauling, it tends to be more hard-faced metals. And in the mid-range, you'll see the ceramics and the overlaps. But typically, in the front end, the process seems to be driven more by the hard-facing and thermal spray systems. And as you move to the back end, it tends to be more elastomers and reinforced coatings. That's based on wear resistance, chemical resistance, and the resistance to gouging wear, grinding wear, scratching wear, or erosion corrosion. Now, in an example here, I want to focus on, this is a classic example of a carbon-in leach tank in a gold processing area. This is an example of two different maintenance practices, both utilizing a protective coatings technology. But if the intent is to reduce downtime related to the maintenance and we want to increase process equipment availability, then anything that we can do to keep that piece of equipment in service longer is to our benefit. And we want to look at minimizing the cost overall. So on the left-hand side, you can see a preventative approach. And if you compare preventative and reactive, at the construction phase, they both had the same initial cost. So building the structure and doing the initial lining installation all assumed the same cost. On the preventative side, you can see they've implemented a 3-year inspection, periodic inspection, to do preventative maintenance approaching. If you then incorporate a 5-year maintenance cycle, an 8-year maintenance cycle, a 10-year maintenance cycle, a 15-year maintenance cycle, and a 20-year maintenance cycle, you can see you're spending less money over time to achieve the same 20-year service life. If you go to the reactive approach, here you can see where they did the initial construction. They did not do a 3-year interim inspection. They went straight from construction to a 5-year cycle and then a 10-year cycle with no intermittent inspections or preventative repair approaches. So they just let the wear factors or the corrosion factors multiply and build on top of one another until at the end of that 20-year cycle, they've spent roughly 50% more money to protect the same vessel. So if you use a coating system properly as this in the effort to increase the mean time between repair, and you use a preventative approach whenever possible, you can reduce life, you can extend life and reduce costs of that piece of process equipment over the life of the equipment. Now, in summary, coatings definitely have an impact on the mining and ore processing operations. There are numerous coatings that are out there. They can be used to extend the life of the component or structure. They can decrease equipment downtimes, increase production. They can reduce your spare parts carrying cost if you do this properly, if you choose the correct materials to get that life. And overall, that will decrease your maintenance and operational costs over time. Now, there are certain calls to action that I'd like to ask anyone who's involved in this to take into consideration. We'd ask that you evaluate the rate of or the impact of wear and corrosion on your productivity through a full plant assessment. Identify the worst actors first. Identify what is the impact of wear and corrosion on your productivity. Once you do that assessment, then you'd want to consider the pros and cons of the various wear and corrosion resistant technologies that we've discussed today. Once you've done that evaluation, we'd like you to complete that evaluation, and then we'd like you to implement and review for effectivity over time. That means going back and doing periodic inspections to see if your selection has been appropriate and is providing you the wear life. And then if it's not, refine for improvements. These are some of the best practices that are being utilized in the industry today. The materials that are being used are being advanced on a regular basis. They are moving more and more towards thermoplastic materials to non-metallic materials. The ability to get higher and higher hardness alloys is increasing. So as you look at your various technologies that are available to increase the mean time between repair, take into consideration the type of wear, what are the environments associated with that wear, and then you can make a suitable and correct material selection and end up with, hopefully, the desired results of increased productivity and increased mean time between repair. Victor's asked, do we have a comparative cost chart between the technologies? If you're looking at a comparative cost chart, Victor, what I would do is I would propose a chart that would actually have the total installed cost amortized over expected life. Oftentimes, the invested cost Sometimes the invested cost can be high, but the life is longer. In that case, you want to look at the amortized lifetime costs. But pure materials cost, pure installation cost, it's relatively easy to come up with that. We do have a comparative chart that looks at weld overlay and some of the pros and cons compared to thermal spray, compared to rubber-based systems, and we can provide that. I want to thank you again for your time and attention today. This webinar, as I said, will be posted up. Our marketing communications group will get this posted out to everybody who signed up, so you can download it and use it as a resource in the future. And I want to thank you very much for your time and attention today, and have a great week.